So thank you for introduction. I'm Takao Murakami from AIST. And in this presentation, I'd like to introduce utility-optimized local differential privacy. So first, I briefly explain the outline of this work. Recently, personal data are increasingly collected and analyzed for various purposes. For example, a large amount of location data can be collected and analyzed to find popular sightseeing places or visualizing population distribution. And for another example, personal data such as age, income, and marital status can be collected via survey sampling, and a joint distribution like this can be computed to specify target customers. So these data are very useful for users or companies, but there is a serious privacy issue. For example, personal data contains sensitive information such as home, hospital, and income. So we need to strongly protect users' privacy, and the problem is how. And to protect users' privacy, local differential privacy, LDP, has recently studied. LDP is a variant of differential privacy in the local model. And in the local model, a user obfuscates her personal data, such as locations, response in a survey, by herself. In other words, we don't assume a trusted third party. And this is a definition of epsilon LDP. Obfuscation mechanism Q provides epsilon LDP if we have this inequality. And it means that the attacker can't estimate the original data X from noisy data Y with a certain degree of confidence. And epsilon is called privacy budget. And when epsilon is small, the original data X is strongly protected. And examples of Q include randomized response and RAPPOR developed by Google. And the feature of LDP lies at its strong privacy. First, privacy is protected against attackers with any background knowledge. And this is a property of differential privacy. And second, the original data are not leaked from the database. In the centralized differential privacy, there is a risk that all of the personal data are leaked from the database by illegal access. On the other hand, in local differential privacy, the original data are not leaked from the database because we don't assume a trusted third party. And LDP has also been used by some companies. For example, Google estimated a relative frequency of Chrome home pages via RAPPOR. And Microsoft estimated a histogram of daily application usage via its own mechanism. And both of them are related to a distribution estimation task. And here, each user sends noisy data, and the data collector estimates a distribution of the original data, P. And by using LDP as a privacy measure, we can strongly protect users' privacy. However, there is a utility issue in LDP. Unfortunately, the original distribution P may not be accurately estimated in practice because LDP adds too much noise. LDP regards all personal data as equally sensitive and causes excessive obfuscation and the loss of utility. In other words, there are a lot of non-sensitive data in practice. And to explain more about this issue, let's consider a question such as, have you ever cheated in an exam? Obviously, yes is a sensitive answer to this question, while no is not sensitive. And we want to estimate the original distribution P, but in this example, 30% of the target population have really cheated in an exam. So we need to protect these users' privacy. And a classical solution is to use Warner's randomized response. This mechanism flips both yes and no with probability p. Then both answers may come from yes or no, so users' privacy is strongly protected. And in fact, this mechanism provides epsilon LDP. And the second solution is to use Mangat's randomized response. This mechanism always sends yes as it is and flips no with probability p. Then the answer yes may come from yes or no, so sensitive users' privacy is protected. And also, no is always come from no, so the original distribution can be more accurately estimated. However, this mechanism doesn't provide epsilon LDP for any epsilon because LDP assumes both yes and no as equally sensitive. So a natural question would be, how can we guarantee LDP for only sensitive data? And we made some contributions on this issue. In this work, we focus on a discrete distribution estimation task because it is a popular application, and introduce ULDP, utility optimized LDP, to guarantee LDP only for sensitive data and achieve high utility. And we focus on a common mechanism scenario where the mechanism is common to all users. And we propose ULDP mechanisms that provide much higher utility than randomized response and RAPPOR. For example, we outperform them by 1 or 2 orders of magnitude. And we also proposed a mechanism for personalized mechanism scenario where the distinction between sensitive and non-sensitive data can be different from user to user. For example, a location of home can be different from user to user, and we can deal with such scenarios. But here, we only explain the common mechanism scenario for lack of time. So for details of the personalized mechanism, please see our paper. And in this work, we also assume that each user sends a single datum, and each user's datum is independent. This is a very simple assumption, but it is reasonable for various kinds of data, such as locations, age, and gender. And we leave the case of multiple data per user as future work. So this is the outline of this work. So next, I will introduce ULDP. In ULDP, we first divide the set of input data X into the set of sensitive data Xs and non-sensitive data Xn. And we also divide the set of output data Y into the set of protected data YP and invertible data YI. Then, intuitively, ULDP provides LDP for only sensitive data and doesn't protect non-sensitive data. So by protecting minimum necessary data, we can achieve high utility. More specifically, this is a definition of ULDP. Obfuscation mechanism Q provides excess YP epsilon ULDP if we satisfy these 2 conditions. First, for any invertible data Y, there exists a unique non-sensitive data X such that the transition probability is positive for X and 0 for any other input data. In other words, any invertible data is invertible and reveals the original non-sensitive data. And the second condition states that we provide epsilon LDP for protected data. Here, the output set corresponding to XS is restricted to YP, so we can provide epsilon LDP for sensitive data. And the feature of ULDP lies at invertibility and epsilon LDP for protected data. By invertibility, we can accurately estimate the original distribution, and by LDP for protected data, we can strongly protect sensitive data. For example, Manga's randomized response provides epsilon LDP for protected data, and the invertible data XO reveals the original non-sensitive data. So this mechanism provides ULDP. And we also showed some basic properties of ULDP, such as compositionalities and the immunity to post-processing. So for more details, please see our paper. Okay, so next, I will introduce some ULDP mechanisms, such as utility-optimized randomized response and utility-optimized rapport. The basic idea of our ULDP mechanisms is to use epsilon LDP mechanism, such as randomized response and rapport, for sensitive set XS and YP. And then we set probabilities from Xn to provide ULDP. And here, we can use any LDP mechanism for XS and YP. So in this work, we use randomized response and rapport for XS and YP. So our first mechanism is URR, utility-optimized randomized response. URR is a generalization of Manga's randomized response to k alphabets, where k is the size of x. And then we use ks randomized response for xs and yp, where ks is the size of xs. Then we set probabilities from xn, that is p3 and p4, to provide ULDP. And this mechanism provides XS, YP, epsilon, ULDP. And our second mechanism is URAP, utility-optimized rapport. So I first explain the basic one-time rapport, which was developed by Google. Rapport is an epsilon LDP mechanism for k alphabets, and it maps xi to ei, the ith standard basis vector, and then flips each bit of ei with probability p. And based on this mechanism, we construct URAP. And this is URAP. First, we assume that the first ks alphabets are sensitive and remaining alphabets are non-sensitive without loss of generality. Then it is important to note that if xi is sensitive, all of the right elements of ei are 0, like this. Based on this, we use rapport for left elements. And we flip 1 in the right element to 0 with probability p2. And this mechanism also provides XS, YP, epsilon, ULDP, where YP is the set of vectors whose right elements are 0. And we theoretically analyzed our ULDP mechanisms. Here, we analyze the L1 loss between the empirical estimate p hat and the true distribution p. And we assume that ks is much smaller than k and analyze the expected L1 loss in high privacy and low privacy. And here are the results. And we can see that in low privacy, URR achieves almost the same utility as a non-private mechanism that doesn't add any noise. And in high privacy, URAP, we also prove that in high privacy, URAP is order optimal among all ULDP mechanisms. And we also analyzed the L2 loss and obtained similar results. So in summary, in low privacy, URR is effective, and in high privacy, URAP is effective. And we also show this in our experiments. Okay, so I go on to our experimental results. In our experiments, we used 2 real data sets, the Foursquare data set and the US Census data set. But here, I explain only Foursquare for lack of time. The Foursquare dataset is a location dataset which contains 300,000 check-ins in Manhattan. And here, we assume each user sends one location, and we divided Manhattan into 25 by 25 regions at regular intervals. So the number of regions K is 625. And we assumed 15 regions, including hospitals, as sensitive regions. And as a true distribution P, we used a frequency distribution of all users. And then we selected a half of all users as those who sent noisy data. And we used the empirical estimation method and the EM reconstruction method to estimate a distribution from noisy data. And here we have the results. This is a relationship between epsilon and total variation. And RR is randomized response, and RAP is rapport. So the red line represents the performance of the existing mechanisms, and the blue lines represent the performance of our mechanisms. So we can see that our mechanisms outperformed randomized response and rapport by 1 or 2 orders of magnitude. And we also examined the relationship between Ks as the number of sensitive regions and total variation. Here, we randomly selected Ks sensitive regions from all regions, and this is the result. The left figure is the performance in high privacy, and the right figure is performance in low privacy. So we can see that our URAP provided the best performance in high privacy, and URR provides almost the same utility as a non-private mechanism in low privacy. So in conclusion, we can say that our theoretical results also hold in our experiments. So let me summarize this talk. In this work, we proposed ULDP mechanisms which provide much higher utility than randomized response and rapport when there are a lot of non-sensitive data. And as future work, we'd like to consider the case of multiple data per user, because in this work, we assume that each user sends single data, but when a user sends multiple data, there might be a correlation between sensitive and non-sensitive data. So sensitive data might be inferred from non-sensitive data, so we'd like to extend ULDP to protect such correlated data. Okay, so thank you for attention.
We've got a bit of time for questions if people want to ask one. Perfect.
Thank you very much for the nice presentation and the nice work. I had a small question regarding how trivial or non-trivial it is to compose a system with several different values of epsilon, such that you can tune for each type of information how private it is, such that you can find for each type of information the sweet spot between utility and privacy.
Sorry, your question is about how to set epsilon?
And so if I understand correctly, then in the systems you presented, you chose one value of epsilon, right?
Yeah.
And I was wondering how easy or not it is to have multiple values of epsilon for this, different types of information in the same system.
Okay, thank you for your question. Yeah, here we simply assume that we can divide personal data into sensitive data and non-sensitive data, so all or nothing. But of course, it might be possible to extend our ULDP to assign different epsilons to different levels of sensitive data. So we'd like to consider it as our future work. Thank you.
Thank you.
I'll ask one more question while our next speaker comes up and sets up. So you pointed out the future work. There might be multiple data points that are correlated, so you can't protect that. So that means Google shouldn't switch to your thing yet. Do you have any intuition about what the next step would be? How do you solve that future work?
Yeah, I think this future work is a very challenging future work. Actually, we are planning to use pufferfish privacy. Pufferfish privacy is generalization of differential privacy to protect correlated data. So, for example, if there is a strong correlation between sensitive and non-sensitive data, we add noise to non-sensitive data as well as sensitive data. So by incorporating pufferfish privacy into ULDP, I think we can protect correlated data. So, yeah.
Let's thank the speaker once more.